Yeah, can you see my screen?
Yes, sir.
I'm clear audible now.
Yes, sir.
Okay, this is the problem which we have solved. So what we have discussed is the interface flux in mass transfer and momentum transfer in last class. Before that, in one class we have discussed interface flux in heat transfer. So what we have done is in this interface flux, we try to understand why friction factor, heat transfer coefficient, and mass transfer coefficient is actually needed in a discussion when we have Newton's law of viscosity, then Fourier law of heat conduction and Fick's law of diffusion. Still, this is needed. So that need of heat transfer coefficient, mass transfer coefficient, and friction factor, and then we try to physically interpret because whatever the complex nature of flow characteristic at the interface is combined together and compiled that transport in a transport property. So, that transport property is named as the heat transfer coefficient, mass transfer coefficient, and friction factor. So, we try to correlate with a basic property, fundamental property like viscosity, thermal conductivity, and diffusivity, and we got the physical interpretation of this thing actually. Anybody has any doubt over here? So exactly now what in this class is actually this is you can say concluding class for the base of transport phenomena. So whatever this in last say 7-8 classes we have tried to discuss all correlating heat, mass, and momentum. This will create a base of your transport phenomena. This is not just one subject. These are actually in fact heat transfer, mass transfer, and momentum transfer. This is the best overview over which we'll travel now we'll further go in details, and there is no limit up to what detail you can go in every aspects of this transport phenomena. So this is the best. So what is the next approach? So it will be exactly similar as we have done in molecular transport. Initially we have discussed three laws. Newton's law of viscosity, Fourier law of heat conduction, and Fick's law of diffusion. And then what we have done? Roll number 99.
Yes, sir.
So what we have done after that, after discussing these three laws in molecular flux, what we have done?
Convective flux. Convective flux we discussed.
No, before that, before going into convective flux, we have analyzed this molecular flux in detail.
Yes, sir.
What we have done in there?
So we tried to establish a relationship between all these three.
All these three. So what exactly? What is the approach we have taken?
Like molecular flux equal to diffusivity into gradient of quantity per unit volume. So for any transport phenomena like momentum transfer, energy transfer, flux transfer, the basic formula would be same, like molecular flux equal to diffusivity into gradient of volume.
So in turn, what in a way what we got actually, we got some important output from that discussion.
Yes, sir.
Yeah, what is that?
Sir, for momentum transfer, sir, tau A equal to mu into dV by dt, dV by dx.
So that was the initial observation, similarity. So what we have done is we have tried to improve the similarities. So we were telling that Newton's law of viscosity is similar to Fick's law of diffusion is similar to say Fourier law of heat conduction. Then we have modified little bit and converted into appropriate form and established this similarity. Then we got a common transport property which is diffusivity. That is what first thing we have done. Okay, they are in molecular flux actually, and then ratio of two diffusivity we got a dimensionless number. Okay.
Yes, sir.
So here also we'll get we'll approach same same way. In same way here also we'll try to make these equations similar Okay, and see what kind of dimensional less number we will get here. So here you can see interface flux. This is the discussion on interface flux. So this is the equation, finding equation we have used in interface flux in momentum transfer. Now this I can rearrange this equation in this form. Tau w equals to half rho VCH, characteristic velocity. Characteristic velocity means velocity which can be a property of the system. Okay, which can be a property of system, that is called as a characteristic velocity. And moreover, this can be written like this: 1 delta ch. This is gradient of delta ch, and this delta ch will be delta ch minus 0. At boundary, velocity will be 0 actually. So velocity will be 0. That is what this will be there. This delta ch. So I can write same equation. Same equation will be half rho VCH square into R. So this VCH can be written like VCH into VCH, and one VCH can be interpreted as a gradient. So this is one and same thing, as we are assuming that no slip boundary condition at the wall. At no slip boundary condition, delta VCH will be equals to VCH, and this is just a rearrangement. Similarly, so we were discussing interface flux in heat transfer. Interface flux in heat transfer. So where we got a Newton's law of viscosity. So Newton's law of viscosity. So here this can be written like delta T. Okay, delta T. So this is the driving force, and this is the transport property. So here this delta VCH is the driving force, as we know that temperature is similar to velocity. So this is the driving force, and this is, you can say, transport property overall, including friction factor. Friction factor, velocity, density, and this constant divided by 2. This is interpreted as a one transport property. Okay, similarly in mass transfer, which is the equation which we come across in mass transfer? Roll number 78. 78.
Yes, sir.
Yeah, what is the equation we come across in mass transfer in interface flux?
Yes, sir. NAW equals to Kc into delta Ca.
What is that name of the equation?
Slattery.
Slattery equation, or Newton's law of mass transfer. So this
Yes.
will be NAW equals to Kc into delta C. Okay, this will be delta C. So this can be written like, so here I can say this is the driving force. This is the driving force, and this is actually mass transfer coefficient. So this is clear. So what we have done in molecular momentum flux hereafter. Here, roll number 30. Now these three equations are similar. Why these are similar? Why these are similar? Because all three are discussing interface flux. This is discussing interface flux in momentum transfer. This is discussing interface flux in heat transfer, and this is discussing this thing, interface flux in mass transfer. So these are similar. What is next step? Roll number 30. Roll number 30. Roll number 93. Roll number 93. Roll number 76. So what we can do hereafter? What exactly we have done in molecular flux?
In molecular flux, sir, we have obtained formula, sir.
Yeah. Now these three equation is showing interface flux in
Similarity
momentum
between
transfer,
all
interface flux in heat transfer, interface flux in mass transfer. These equations are similar. Now thereafter,
Yes, sir, yes.
what can be a step? What we can do? And this is exactly we have followed in molecular momentum flux also.
Yes, sir. Sir, physical interpretation.
Not physical interpretation. Roll number 76. Roll number 71.
Sir, we will write the difference in quantity in per unit volume.
Very good, very good. Because here you can see this is the driving force. This is what I am discussing is. So here I am discussing, you can say mass or moles per unit area per unit time, and this driving force is also moles per unit volume. A driving force, a difference of moles per unit volume. But here this is heat per unit time per unit area, but here driving force is in terms of temperature. Similarly, this is actually momentum per unit time per unit area, and this driving force is in velocity. So as here you can see, this is you can say flux of quantity. Okay, flux of quantity, and driving force is a, you can say, quantity per unit volume, difference of quantity per unit volume. Similarly, I can rearrange here also. Okay, similarly, I can rearrange here also. What can be done? Here, roll number 6.
Yes, sir.
So, what can be done in heat transfer? So, you got the point. Here, this is quantity per unit volume or moles per unit time per unit area. Okay, per unit time per unit area, and this driving force is in the form of moles per unit volume, but here it is heat per unit time per unit area, and driving force is in the form of temperature. To bring here quantity per unit volume, what can be done?
So we can write a general equation in like of in so right we have written earlier also that interface plus is equals to difference in quantity by volume into transfer
Yeah, but
coefficient.
how to rearrange quantity per unit volume using temperature?
Mm,
No, okay, sir. Okay.
Sorry, sir.
Yeah, this is how to bring quantity heat per unit volume using temperature.
Sir, we can do one thing. We can, sir. Uh, just a second, sir. Sir, just a minute.
What we have done in molecular transport.
So we can divide and multiply by density and that heat capacity.
Very
That
good. Heat capacity. Similarly, here also, instead of velocity, if I want a, you can say momentum per unit volume, what can be done?
Sir, again we can divide and multiply by instead of heat capacity. In that we can do heat capacity. Here we can multiply and divide by density itself.
Very good, very good. This is exactly we have followed in molecular flux. Okay, so this is a finding equation, and this equation 2 is a Newton's equation. Newton's equation for you can say Newton's cooling equation, equation, and this is Slattery equation. So now these three equations are similar. Even though this is similar, as I am telling, this is indicating a flux of moles, and here I have driving force in terms of moles per unit volume. This is indicating flux of heat. So certainly this should be here. If I can bring a heat per unit volume, driving force in terms of heat per unit volume, that will be more closer to this equation. Similarly, this is flux of momentum. If I can bring a gradient of a momentum per unit volume, that will be more closer to this equation. So multiplying, okay, so this is actually, this I can write a generalized equation: interface flux equals to transfer coefficient difference in quantity per unit volume. Okay, that will be a transfer coefficient. So this is not in the form actually, so I can bring in that form. So as told by roll number 6, it is rho into Cp. I can adjust rho into Cp. So this will be heat per unit volume. So this will be heat per unit volume. And similarly, in momentum transfer, I can multiply rho divided by rho, and this will be a momentum per unit volume. Now these three equations are more closer to each other. Okay, more closer to each other. So these are the constant which is called as a transfer coefficient. So half friction factor into velocity. So half friction factor into velocity in momentum transfer is called as a transfer coefficient. H, okay, H which is generally termed as a heat transfer coefficient, but that is not a, you can say, generalized transfer coefficient. H by rho Cp is a generalized transfer coefficient. Similarly, Kc is a mass transfer coefficient. So this we can call it as a, so this delta Ch represent rho into V infinity multiplied by 0 as velocity at the interface will be 0. This delta rho Cp into T will be rho Cp Tw wall minus rho Cp bulk temperature, and delta C, this will be driving force. So these are all are called as a generalized transfer coefficient. What is it called as a? So till now H we are calling as a heat transfer coefficient, Kc is a mass transfer coefficient, and friction factor is a momentum transfer coefficient. But now we have bring all these three equations more closer to each other, and these are called as a transfer coefficient. Okay, these are called as a transfer coefficient or generalized transfer coefficient. You can call it as a generalized transfer coefficient. What is that? Half friction factor into velocity, h by rho Cp, and this Kc is a mass transfer coefficient. So these are called as a generalized transfer coefficient. So actually H is not a heat transfer coefficient. So you can call it as a H by rho Cp is a generalized heat transfer coefficient. Generalized in a sense, when I am discussing transport phenomena, heat transfer is a one part of transport phenomena, mass transfer is a part of transport phenomena, and momentum transfer is a one part of transport phenomena. So Kc is a generalized mass transfer coefficient, H by rho Cp is a generalized heat transfer coefficient, half friction factor into velocity is a generalized momentum transfer coefficient. This is clear to everybody? This is clear to everybody? Now you can see what is the unit of mass transfer coefficient. Here, roll number 10. Roll number 10.
Yes, sir.
What is the unit of mass transfer coefficient?
Mass transfer coefficient. Moles per unit volume.
Mass transfer coefficient.
Meter per
Go to
second.
this equation. What is the unit of this? NaW?
The NaW is moles per unit area per unit time. So it will be
Moles per unit
meter
area
square
per unit time. What is the
Yes,
unit of
moles
this
per
delta Ca?
It will be moles per unit volume.
So what will be unit of Kc?
Meter per second.
Meter per second. So what is the unit of H by rho Cp?
It will also be meter per second.
What will be unit of half friction factor into VCH?
It will be also same meter per second.
Very good. So this is what exactly. So these are having all same unit, meter per second, meter per second, meter per second. Okay, these are called as the generalized mass transfer coefficient. Now certainly this, what is the unit of friction factor? Roll number 10.
Yes, sir.
What is the unit of friction factor?
It will be unitless.
Unitless. So now this quantity is getting a unit just because of this velocity. Okay, meter per second. This quantity is getting a unit because of this H, rho, Cp. All three are involved in the dimension. Kc is as meter per second. So whenever we are discussing a dimensionless number, this doesn't play any role. Half is a constant. Similarly, friction factor is also dimensionless. Okay, dimensionless quantity. So that doesn't play any role when we are discussing a dimensionless quantity. Okay, dimensionless quantity. So from this we can take VCH is a representative of generalized momentum transfer coefficient. So what is this velocity? Velocity is kind of driving force also, and that will also represent a generalized transfer coefficient in momentum transfer, representative of generalized momentum transfer coefficient. So velocity played a double role in momentum transfer. When interface flux, in interface flux, so this it will give you, you can say, driving force also. Okay, in driving force also velocity play a role. In transport property also it will play a role. So, and now what will be ratio of generalized heat transfer coefficient divided by generalized, you can say, representative of generalized momentum transfer coefficient, H by rho Cp into V. Have you heard of this dimensionless number? Here, roll number 20. What is this dimensionless number? Roll number 20. Roll number 25.
Yes, sir. 20, sir. Sir, this is sir velocity.
No, sir. Okay, sir. Okay from my side. So, what is this dimensionless number? Roll number 20.
Yes, sir. So,
What is this dimensionless number? H by rho Cp into V infinity, VCH.
VCH, sir. Sir, VCH is a velocity of
Whether this is the dimensionless number, first of all. Yeah, can
sir
you tell
whole
me your,
entire one.
yeah?
Sir, Aviral.
Aviral. Roll number 20, na?
Yes.
Yeah.
Yes, sir.
So whether this is the dimensionless number?
Sir, the entire thing, sir, has unit of meter per second. Sir. No.
This entire thing.
No. Yes, sir. Now it is that. Now it is sir dimensionless.
So what is
Yes, sir.
this dimensionless number is called as a? This is the
Sir,
Stanton number for heat transfer.
sir, Stanton number. Yes, sir.
Okay. So what is the physical significance of
Yes, sir.
Stanton number now? What is the physical significance of Stanton number?
So physical significance will be sir. Sir, momentum transfer, sir, advective one, sir, it represents that.
Only momentum transfer it will represent.
No, sir, advective momentum transfer.
Huh?
Sir, advective momentum transfer, sir. No. Sir, it will represent, sir, heat by, sir, H by rho Cp will represent heat and VCH will be, sir, momentum. So heat upon momentum, sir.
Yeah. So Stanton number represent the ratio of generalized transfer coefficient for heat transfer to generalized transfer
Yes,
coefficient
sir,
for
and
momentum
momentum
transfer.
transfer.
So this is kind of
Yes, sir.
representing a interface heat transfer divided by interface momentum transfer. So you can say
Momentum
overall,
transfer.
okay, overall heat transfer at the interface, and this will be overall heat
So
momentum
momentum
transfer
transfer.
at the interface. Okay, this is the physical
Yes.
significance of Stanton number. This already we have done. Okay, this is
Yes.
this is already we have done.
Yes.
Actually, already we have done. Where we have done?
Yes.
Where we have done? Similar thing, we got a physical interpretation of Prandtl number, Schmidt number, and Lewis number. Same thing we have followed here also. Okay, so what next? The ratio of Kc divided by Vch. What is this? This is the Stanton
Yes.
number for mass transfer. Roll number 30.
Transfer.
Roll number 30. Roll number 35. 35.
Sir, he is absent, sir.
Roll number 40. Roll number 40.
Yes, sir.
Yeah. So what is the physical interpretation of standard number for mass transfer?
Sir, physical interpretation.
Huh?
Yes, sir. Sir, this will be relating mass transfer, generalized mass transfer coefficient, and momentum. Generalized mass transfer coefficient. Generalized transfer coefficient for momentum transfer. So if the standard number is high, then we can say.
सिर्फ वो अगर रेडी है तो बहुत बढ़िया रहेगा.
Hello, sir.
हाँ, tell me.
Sir, this will be relating the generalized transfer coefficient for mass transfer and momentum transfer, sir.
Very good. So what can be a next step? What we have done in momentum transfer, this molecular flux when we are discussing. Yeah, what is next?
Sir, as we did in molecular flux.
Okay, sir, I will leave the meeting. Thank you, sir. Thank you. Okay, sir. Yeah. So what is this is now interface flux. So we got now generalized definition for interface flux. So what is generalized definition for interface flux? Transfer coefficient divided into difference in quantity per unit volume. Similarly, we have molecular flux, which is diffusivity into gradient of quantity per unit volume. Now this is also flux. Okay, this is also flux and this is also flux. Certainly, this ratio of two fluxes are again dimensionless number. Okay, again dimensionless number. So and this gradient of quantity per unit volume will have unit. Okay, difference in quantity per unit volume divided by characteristic length. This already we have discussed. So gradient of quantity per unit volume will have a unit. Okay, unit of difference in quantity per unit volume divided by characteristic length. Now combining A, B, and C. Okay, so dividing. So you can say this is the flux, this is also flux. I can divide this and get a dimensionless number. And rearrange this. Okay, rearrange this gradient of quantity per unit volume will be equals to difference in quantity per unit volume into characteristic length. Okay, so this I can say combining equation A, B, and C. So interface flux divided by molecular flux will be equals to transfer coefficient. This is transfer coefficient. This will be diffusivity. This will be diffusivity, and this is difference in quantity per unit volume, and this will have unit difference in quantity per unit volume divided by characteristic length. So this characteristic length will go upside actually on numerator. So it will be transfer coefficient multiplied by characteristic length multiplied by divided by diffusivity, and this represents the ratio of interface flux to molecular flux. Is it clear? So this is clear. Roll number 45.
Yes, sir.
Yeah, this is clear.
Yes, sir.
So now what is the dimensionless number in momentum transfer? Transfer coefficient. What is transfer coefficient in momentum transfer?
So KC.
Momentum transfer.
Oh, sorry, sir. So it's half F into VCH, or we can just say VCH.
VCH. What is characteristic length in momentum transfer? So you can say L. And what is diffusivity in momentum transfer?
So mu.
Mu is the diffusivity in momentum transfer. Momentum diffusivity.
Sorry, sir. Mu by rho.
Mu by rho. What is the dimensionless number now?
So it will be
What is the dimensionless number?
So VCH into LCH divided by VCH LCH rho divided by mu.
What is the dimensionless number? Rho VL divided by mu. Rho
So Reynolds
VD.
number.
dV rho by mu. What is the dimensionless number?
Oh, so Reynolds number. Reynolds number.
So don't you recall this Reynolds number? I'm talking about characteristic length, transfer coefficient, mu by rho is there. So what is the similar dimensionless number in heat transfer then? Yeah, I'm talking to you only.
Yes, sir. So the transfer coefficient would be.
Transfer coefficient will be H by rho Cp.
Yes, sir.
Generalized transfer coefficient. Characteristic length will be L, and heat diffusivity will be K by rho Cp.
Yes, sir.
So Hd by K. What is that dimensionless number?
So it will be Nusselt number.
Nusselt number. Similarly, in mass transfer, what will be the dimensionless number?
So Kc into L
Divided by DAB. KCL divided by DAB. What is that dimensionless number is called as?
Sherwood number.
Sherwood number, or it is also called as a Nusselt number for mass transfer. So these are the three numbers, okay, for momentum transfer. So you can anyway, this doesn't have any role to play in this thing actually, dimensionless number. So this will be transfer coefficient will be half friction factor into velocity mu by rho. So interface flux. So Reynolds number is kind of what is the physical. Now looking at the transport phenomena point of view. First, I'm studying three subjects together: heat transfer, momentum transfer, and mass transfer. So, what is the physical interpretation of Reynolds number? Physical interpretation of Reynolds number will be it is the ratio of interface flux or total flux at the interface flux divided by molecular flux. Okay. So it is the ratio of total flux at the interface divided by molecular flux, and along with friction factor and some constants. So it will represent the interface flux divided by molecular flux, and this will be half into Reynolds number. Similarly, in heat transfer, so transfer coefficient will be H by rho Cp and diffusivity will be K by rho Cp. So ratio of this will be HL by K. HL by K. So this LCH, characteristic dimensions of flow through pipe. When we are discussing flow through pipe, characteristic length will be a diameter. Okay. When we are discussing flow through pipe, this characteristic length will be a diameter of the pipe. So similarly, flow over flat plate, it will be the length of the pipe parallel to the flow. That will be a characteristic length. So this will be HL by K. So this is nothing but the Nusselt number. Similarly, in mass transfer, so transfer coefficient is Kc and diffusivity is DAB. So ratio of this interface flux divided by molecular flux will be Kc into LCI divided by DAB. This is called as a Nusselt number for mass transfer or Sherwood number. So this is what dimensionless number we have. So similar dimensionless number we have discussed: Prandtl number, then Schmidt number. This is Nusselt number for mass transfer, Sherwood number for Stanton number for heat transfer, and Stanton number for mass transfer. This is H by rho Cp, which will be equals to Nusselt number divided by R into Pi. So I can rearrange this H by rho Cp VCH, and this Stanton number for heat transfer, rearranging everything. So you can rearrange Nusselt number divided by Reynolds number into Prandtl number. Similarly, Stanton number for mass transfer, rearranging this, we can get it will be equals to Sherwood number divided by Reynolds number into Schmidt number. So this is all dimensionless number we got actually. So now this is you can, as I told, so this is the last topic. Conclusion of the discussion that similarity in heat transfer, mass transfer, and momentum transfer. How we have gone into this is we have started with definition of flux, and then slowly we have built up this information. Just I will summarize everything. Now whatever doubts you have, so you can raise your doubts, confusion, everything. I will summarize what we have done. So what we have done is we have started with a definition of flux. This is first class. In first class we have started the definition of flux, and then we have categorized that into two parts. One is a molecular flux, another one will a convective flux. This is the two fluxes we have discussed. Then in molecular flux we have discussed Newton's law of viscosity. In molecular flux in heat transfer we have discussed Fourier law of heat conduction, and molecular flux in mass transfer we have discussed Fick's law of diffusion. Okay, Fick's law of diffusion. So this was actually molecular flux equals to transport property into gradient of driving force. This driving force was uneven. Okay, driving force was uneven in all these three. So but in mass transfer it is gradient of quantity per unit volume. So we have tried to make similarize, and this gives a three constant. So molecular flux, transport property into gradient of driving force. So it gives viscosity in momentum transfer, thermal conductivity in mass transfer, and diffusivity in thermal conductivity in heat transfer, and diffusivity in mass transfer. Then we have tried to bring these three equation more closer, so that this gradient will look like similar gradient of quantity per unit volume, and all these three transport property are called as the diffusivity. So it will be mass diffusivity, kinematic viscosity, momentum diffusivity, thermal diffusivity, and this is mass diffusivity. So this is what we have discussed. Then we got this ratio of diffusivity in momentum transfer to a heat transfer. It will be rho Cp mu by K, that is Prandtl number. So Prandtl number is a ratio of diffusivity in momentum transfer to heat transfer. Similarly, ratio of diffusivity of momentum transfer to mass transfer, it is mu by rho dAV, Schmidt number. And we have Lewis number, ratio of diffusivity of heat transfer and mass transfer. So this will be a Schmidt number, a Lewis number. Lewis number will be a ratio of Schmidt number and Prandtl number. Okay, so you can rearrange, and accordingly you can get a Schmidt number. Lewis number will be equal to Schmidt number divided by Prandtl number. Then what we have done? So we have introduced this convective flux. So this is the convective flux. So characteristic velocity will be integrated part of this convective flux, and this will be quantity per unit volume. So now this convective flux divided by molecular flux, we have rearranged this. Okay, this gradient of quantity per unit volume, that will have a unit of quantity per unit volume per unit length. So it will give characteristic velocity, characteristic length divided by diffusivity. This is just now we have discussed actually convective flux. So this we got a Peclet number for heat transfer, VCH divided by alpha diffusivity. So Peclet number for heat transfer and Peclet number for mass transfer, there we got. So then we came to interface flux. So next discussion, this is what we have discussed in molecular flux and convective flux. So this interface flux, what is interface flux? Is a total flux at interface. Okay, total flux will be a molecular flux plus convective flux. So as we cannot estimate this quantity, basically gradient of quantity per unit volume, so we got a three new equation. In heat transfer it is Newton's law of cooling, which is giving me heat transfer coefficient. In mass transfer it is a Slattery equation or Newton's law of mass transfer. In friction factor it is a Feining equation, which is discussing me friction factor. F is a friction factor, H is a Newton's law of cooling, and Kc is a Slattery equation. Then again these three equation, okay, these three equation, driving force was slightly uneven. So we have tried to bring that driving force in the form of gradient of quantity per unit volume. Okay, driving force in the form of difference of quantity per unit volume, not gradient. It will be difference of quantity per unit volume. So difference in quantity per unit volume, and we got generalized transfer coefficient. Generalized transfer coefficient in heat transfer. So this H by rho Cp is a generalized transfer coefficient in heat transfer. Half friction factor into velocity is a generalized transfer coefficient in momentum transfer, and Kc is a generalized transfer coefficient in mass transfer. So here we got a two-dimensional number, heat transfer Stanton number and mass transfer Stanton number. So this represent a total interface flux. Total interface flux in heat transfer divided by total interface flux in momentum transfer. Here total interface flux in mass transfer divided by total interface flux in momentum transfer. Stanton number. Physical significance of Stanton number. Then we got a ratio of interface flux and molecular flux. Rearranging the equation, it will give me a transfer coefficient, generalized transfer coefficient multiplied by characteristic length divided by diffusivity. That will represent the interface flux. So interface flux in momentum transfer gives me Reynolds number. So this is the equation, half friction factor rho VCH LCH mu. Okay, so this is the Reynolds number. So then Nusselt number we got, which is HD by K or HLCH by K, and this is Sherwood number. Sherwood number is a KL divided by DAB. So these are the 10-dimensional less number which we have discussed. What are the 10-dimensional less number? Prandtl number, Schmidt number, Lewis number. Then we have Peclet number for heat transfer, Peclet number for mass transfer. Then coming to interface flux, we have Stanton number for heat transfer, Stanton number for mass transfer. Then we have Reynolds number, Nusselt number, and Sherwood number. And overall, we have generalized definition. Generalized definition in interface flux will be a generalized transfer coefficient multiplied by difference in quantity per unit volume. Similarly, molecular flux, okay, generalized molecular flux will be a diffusivity into gradient of quantity per unit volume. So this is what we have compiled everything, heat transfer, mass transfer, and momentum transfer together, and try to study this together. And while studying this together, we come across this 10-dimensional less number and two generalized equation. Okay, anybody has any confusion over here? Yeah, roll number 94, Saransh. Saransh?
Saransh has left the meeting right now.
Okay.
He has some emergency in his family.
Okay. Pratish?
Yes, sir.
Yeah. So any confusion over whatever discussion we have? This is just I have compiled everything in these two slides actually. This is so you can see. So this is one slide and this is one slide. So in these two slides, I have compiled all our 10 class discussion. Almost we are discussing from 8 to 9 class, 9 class, whatever we have covered. So here, so this is the equation, molecular flux into diffusion to gradient of quantity per unit volume. So Prandtl number, Schmidt number, Lewis number, Peclet number. And here interface flux, we have interface flux transfer coefficient to difference in quantity per unit volume. And these are the Stanton number for heat transfer, Stanton number for mass transfer. Then we have, this is Reynolds number, Nusselt number, and Sherwood number. So this is what we have covered till now. So hereafter actually there will be altogether different topic discussion. Okay. Now this is all related. Okay, correlating heat, mass, and momentum. Over these only we will be building. Okay, over these only we will be building. Everything is clear, Pritesh?
Yes, sir.
Okay. Then what we have done is now we will compile the thing. Okay. So molecular flux. We have discussed molecular flux. 3 equation in molecular flux, 3 equation in convective flux. So and 3 equation in interface flux. So these are the 3 equations. So what is this equation? This is Newton's law of viscosity. This is fixed. This is Fourier law of heat conduction, and this is fixed law of diffusion. Similarly, in convective transfer, this will be a rho VV. Okay, convective momentum flux. Rho Cp into T into velocity will give you convective heat flux, and Ca into Vy will give me a convective mass flux. And in interface flux, I have tau W equals to half rho V infinity square into friction factor. This is in heat transfer, heat flux. Okay, interface flux will be a heat transfer coefficient into temperature difference, and this is mass transfer. Interface flux will be a mass transfer coefficient into concentration difference. Now this is, I will say, almost you can say 90% of heat transfer, mass transfer, and momentum transfer will based on whatever design problem you take will be based on this equation only. Okay, 90%, until and unless you go for complex flow, okay, very complex flow, and then transient flow. So if flow is very transient, you are discussing transient zone. So these are the, if you are not discussing transient, steady state, okay, steady state and laminar flow, this will, it will be dominated by molecular flux. If the convective flux is also there, so these are the equations. So together this you can have total flux, and if you have interface, so these are the equations. So it will be dealing with the interface flux. So you observe this. So what is the most important property which will rule this? You can say three subject: heat transfer, mass transfer, and momentum transfer. So here, from here, I will say this is viscosity, thermal conductivity, diffusivity. Then here friction factor, heat transfer coefficient, mass transfer coefficient. Then driving force, in terms of driving force, velocity in momentum transfer, temperature, and concentration. So here also, so this will be velocity, temperature, and concentration. So here also you can see velocity, temperature, and concentration. So these are the most important property in transport phenomena. So overall, so we'll be discussing hereafter evaluation of transport property. Which transport property? Viscosity, thermal conductivity, and diffusivity. Then here we'll be discussing evaluation, how to evaluate friction factor, heat transfer coefficient, and mass transfer coefficient. Then we will discuss the profile equation for velocity. Here velocity, temperature, and concentration. This velocity is important. Here also velocity. Here also it will be velocity, temperature, and concentration. So whole transport phenomena. Now you this slide is giving a syllabus for transport phenomena. So what we are doing in transport phenomena, only the situation will change. So maybe in undergraduate transport phenomena you will handle a simpler problem means steady state problem, laminar problem, and so on. If you go for advanced transport phenomena, you will go in complex problem. So say turbulent flow, and then your transient flow, that you will handle in advanced transport phenomena. But overall transport phenomena will represent a study of viscosity, thermal conductivity, diffusivity, friction factor, heat transfer coefficient, mass transfer coefficient, and this velocity, temperature, and concentration. So now already we have established the relation between these three areas. This is momentum transfer, heat transfer, mass transfer, momentum transfer, heat transfer, mass transfer, momentum transfer, heat transfer, mass transfer. So now these three areas combined together, transport phenomena. So that work is done. Now hereafter what we are going to do in transport phenomena is, so you can say remaining part of transport phenomena, 10% will concentrate on this: estimation of viscosity, estimation of thermal conductivity, and estimation of diffusivity. 10% of remaining syllabus will be based on this: estimation of friction factor, estimation of heat transfer coefficient, estimation of mass transfer coefficient. And remaining 80% of remaining classes will be devoted for this profile equation for velocity profile in momentum transfer, temperature profile in heat transfer, and concentration profile in mass transfer. This is all about transport phenomena, what we are going to cover in next, say 30 classes, remaining 30 classes or so. So maybe out of 30 classes, 3-4 classes will be for this estimation of viscosity, thermal conductivity, and diffusivity. 3-4 classes will be estimation of friction factor, heat transfer coefficient, and mass transfer coefficient. And almost 20 classes will be for estimation, getting the velocity profile in momentum transfer, getting the temperature profile in heat transfer, and getting the concentration profile in mass transfer. This is all about transport phenomena, which we are going to cover in next couple of next, you can say 30 classes also. Okay, so this is what I have concluded everything. What we have covered till today. So if you have any doubt related to whatever topics we have covered till now, because all together from tomorrow onwards we will be discussing all together different ways. Okay, now this base is created up. Okay, whole transport phenomena base is created. Now we will build some information for this, some information for this, and some information for this. Already base is created. Velocity is similar to thermal conductivity, is similar to diffusivity. These three areas are similar, that already base is created and discussed thoroughly. Now hereafter we'll add some information related to this, and related to this. So now hereafter, just what we are going to do in transport phenomena is detailing of the transport phenomena. We are not going to study anything new. We are going to detailing how to get the viscosity, how to get the thermal conductivity, how to get the diffusivity. Detailing will be done. So overall picture of the transport phenomena is already covered. Base is ready. We are ready with base. If you have any confusion, you should not have any confusion, any question over this, whatever topics we have covered. And this is covered in these 3 slides. This is the related to flux, molecular flux, and convective flux, and these are the 5-dimensionless number. This is the interface flux, and this is the generalized equation. These are the 2-dimensionless number, and these are the 3-dimensionless number. And how these 3 areas are similar to each other, already you can go through whatever the cases we have discussed. And this is the compilation of everything. So hereafter we will be discussing this, actually how to estimate these properties and how to get this profile equation for. So anybody